let's just take a moment to just kind of recoup where we were, what we've been doing so far. So we've been talking about sound and waves, and these are the formulas that we have learned about, okay, that we've really been using. You should be very comfortable with these formulas. The speed is equal to lambda f, and you should be comfortable with v of a string, and you should know how to use Doppler's effect, which is FO times this velocity of sound minus plus or minus the velocity of the observer all over plus or minus velocity of the source. And if Vs is toward you, it is negative, and if V of the observer is towards you, it would be positive. Okay, so that's what that is right there. And then need to know how to find the beat frequency. You need to know how to find this for strings and open-ended pipes. And then for a pipe that's closed on one end, this should be V of the sound all over 4L. Okay. And then, of course, we're going to use 331 unless I give you something different. And this is the velocity of a wave on a string, which we would use for stringed instruments. So with that in mind, so we also want to add in the intensity formulas, right? We want to make sure that you understand that the intensity, there's a threshold intensity, and that if you wanted to find the intensity other than the threshold, you know, at some distance, you need to know the pressure, the power rating of the wave, and you need to know the surface area of the wave. And then we could turn that into a decibel by using this formula here, which is the sound level. So we've had all these different formulas, and you need to be able to use them. All right. So with that in mind, just a couple of examples. Let's try this one because we haven't done one of those. 2 tuning forks have frequencies of 526 and 528. The average would literally be the average of those, but the beat frequency would be 528 minus 526, or 2 hertz. So you would hear 2 wah-wahs every second. Okay, so a device called an isolation meter is used to measure the intensity of sunlight, and it has an area of 0.98 centimeters squared and registers 13.2 watts. What's its intensity? So intensity is the power divided by the area in meters squared, right? So the power is 13.2 watts, but this is 198 centimeters squared. So let's convert that. 1 centimeter is 0.01 meters, but we need to square that. So you're really going to be multiplying 198 times 0.01 squared, right? So it's going to go back 2 places and then back 2 more places. So 0.0198 watts. Meters squared. 0.0198 meters squared. 13.2 divided by 0.0198. And that's 600 and 67 watts per meter squared. And here's an example of finding the fundamental frequency. Find the fundamental frequency of a 0.496 meter long tube open at both ends. So it's open at both ends. So we're going to use Fn equals NV all over 2L. Open ends and strings. So that would be 1, because it's fundamental, times 344 meters per second. That's given to you in the problem. Divided by 2 times 0.496 meters. So we're going to have 344 divided by the quantity 2 times 0.496 in quantity equals 346.7 or 347 hertz. What's the second frequency? Well, the second frequency would be 2 times 347 hertz, which would be 694 hertz. If this were a tube that was closed on one end, it would be different. It would be NV all over 4L. It would be 1 times 344 meters per second divided by 4 times 4.496 meters. So that would be 344 divided by the quantity 4 times 0.496, which is 173. And there would not be an F2, there would be an F3. And F3 would be 3 times F1, which is 3 times 173 hertz, which is 419 hertz. Another thing that we've talked about is finding the speed of sound at a different temperature. And that's going to be 331 meters per second plus 0.61 times 51 degrees Celsius. So if I put that in my calculator, 0.61 times 51 equals plus 331, 362 meters per second. Okay, here's a Doppler effect. All right, so it's got a spectator is receiving a 747 hertz tone. Oops. From an oncoming trumpeter who's playing 740 hertz. At what speed is the musician approaching if the speed of sound is 335? So 335. Okay, and we want to know, so VO is going to be 0 because that's the observer and it's just standing there. And this is going to be 335, and it's approaching, and when it approaches, when the source approaches, it needs to be negative. So we're going to subtract off VS. So we're going to have 747 divided by 740, and the hertz will cancel out, equals 335 times 335 minus VS. I'm going to multiply this up here, and that's going to give me 335 minus VS. And then what I'm going to do is I'm going to bring this on the other side. 740 divided by 747. So I'm going to get, if I do this right, minus VS equals whatever 740 is all over 747 minus 335. And then I'm going to have to distribute out that negative. So let's do that. 740 divided by 747 equals, and then I'm going to subtract off 335. So I'm getting negative VS equals negative 334 meters per second, or VS equals 334 meters per second. That easy.